what we want to talk about is eigenvectors and stuff, and in particular diagonalizability. And we define this idea of diagonalizability, which at the outset doesn't seem to really have anything to do with eigenvectors, but the theorem that we're trying to prove says it has everything to do with eigenvectors. The definition of diagonalizability is just that your matrix is diagonalizable if there's some similarity transformation. This is what we call a similarity transformation. Okay? So if there's some matrix P such that A is a P similarity transformation of D, where D is a diagonal matrix. Okay? So A is diagonalizable if it's similar to a diagonal matrix. Okay, that's the definition. That doesn't have anything to do with eigenvectors. But this theorem says, in fact, your matrix is diagonalizable if it's an n by n matrix, if and only if it has n linearly independent eigenvectors. Okay, so the answer to the diagonalizability question is entirely based on eigenvectors. And there's another characterization which goes sort of more deeply into this, which tells you when you have n independent eigenvectors in terms of these multiplicities. Okay? So you've got n independent eigenvectors. If the sum of the algebraic multiplicities is n, so as big as possible, and all of geometric multiplicities are equal to the algebraic ones, so all the geometrics are as big as possible. So you've got n independent eigenvectors when all the multiplicities are as big as they can be. Okay. So we got part way through proving the relationship between, or the equivalence between A and B. Right? So we've shown that A implies B. And now what I want to do is just show that B implies A. Right? So now our ingredients are that we have n independent eigenvectors. So suppose A has n independent eigenvectors. Let's give them names, call them P1, blah, 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 up to Pn. And they've got some associated eigenvalues with them. Right, every eigenvector has to have an eigenvalue. And I'm not assuming here that these are all distinct, right? Lambda 2 could be equal to lambda 7. I have no idea. But for every one of these P's, PI's, there's a corresponding lambda I, such that A PI equals lambda I PI. Okay? But I'm not assuming anything about the nature of these. What we are assuming is that these things are independent. That's all we're assuming. Okay, so what we want to do is use these ingredients to show that A is diagonalizable. And we saw that if A was diagonalizable, then the P and the D that do the diagonalizing were constructed out of eigenvalues and eigenvectors. So what we have to do is work backwards, right? We know what the P and the D should look like. P should be just the matrix you get by using these eigenvectors as the columns. And D should be the diagonal matrix where the eigenvalues are sitting on the diagonal entries. And all we've got to do is show that those two things have the right properties. And that basically almost falls out immediately, right? So D by construction is going to be diagonal. That part's easy. P is going to be invertible, which is all you need. That's the only property that P really needs to satisfy in isolation, because these eigenvectors are independent, right? So P is definitely going to be invertible. D is diagonal, just because we said it was. What you really need to show is that A equals PDP inverse. Okay, so let's define P and D to be what we know they should be if A actually is diagonalizable. So let D be diagonal with diagonal entries lambda 1, blah, 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 lambda n, and let P be this matrix where the ith column is Pi. And since, by assumption, this set is independent, we know P is invertible. All right, so we haven't used anything about the fact that the P's are eigenvectors yet. So now what we want to do is basically show that AP equals PD. Right? If we can get here, then we can just, because P is invertible, we can immediately just multiply on the right by P inverse and get that A is diagonalizable. Okay? So we just need to establish this. So we can start off by just looking at what AP looks like and show that it's equal to PD. And we'll do basically the same thing that we did in the other direction, which was do it column by column. Okay? So let's pick a column. How do you grab out the ith column of some matrix? You multiply the matrix by EI. So this is the AP times EI, but that's A times PEI. PEI is the ith column of P, which we said was called, well, by construction of P, this vector Pi. Right? That's how we made the matrix P. And now we get to use the fact that P is an eigenvector with eigenvalue lambda I. And right, that's about as far as we can, well, as far as we need to go with AP. That's what the ith column of AP looks like. It's lambda I times Pi. And then we can ask the same question, what's the ith column of PD look like? So we saw yesterday, when we thought about it, D times EI is just lambda I EI. All right, because remember, D is a diagonal matrix, so all of its columns are multiples of EI, right? The ith column of any diagonal matrix is a multiple of EI, and the multiple is precisely the diagonal entry. This is lambda I EI. Essentially, by definition of D, you could have defined D to be the matrix such that the ith column is lambda I EI. That's equivalent to saying it's diagonal with diagonal entries lambda 1 up to lambda n. So you can pull out that lambda I. We've got P EI again, which is little Pi. And so this is the ith column of AP. That's supposed to be a P, not a D. AP. Okay? So, ith column of PD is ith column of AP. Therefore, AP equals PD, because that held for every I. No special assumptions on what I is. So now we just multiply on the right by P inverse. And we find that A is this similarity transformation of D, where D is the diagonal matrix of all the eigenvalues. So A and B are definitely equivalent. A and C is a bit trickier. It's not super tricky, but requires a little bit of head scratching. So that's a start problem on the problem set. There's no deep new ideas you need, but you do need to scratch your head a little bit. Okay. Let's do a poll. If I can get this to work, which it appears I cannot. There we go. All right, so true or false? If A is diagonalizable, then there's a unique P such that P inverse AP is diagonal. You look at the proof relating parts A and B of the last theorem. Does that tell you anything about this statement? Okay. All right, it's pretty even split, 40 to 60. So let's go back and look at what we just proved. Okay, so we said let A have n independent eigenvectors, right? Now, we know that A is diagonalizable if and only if it has n independent eigenvectors. So this is basically, we could have started with the assumption that A is diagonalizable and therefore it'll have n independent eigenvectors, but we're just starting by saying, let's say A has n independent eigenvectors. As soon as we take n independent eigenvectors, we can make the matrix P and we can make the corresponding matrix D, right? And then we've shown that A is diagonalized by this P. But if A has n independent eigenvectors, then I could multiply all of those eigenvectors by 7. Now we'd still have a collection of n independent eigenvectors, right? So then I would have P where I've multiplied all my columns by 7. No, we'd still have a P that diagonalizes my matrix. D wouldn't change. The 7 would pop out as a 1 on 7 and the inverse of P, right? So there's nothing unique here because as soon as you've got n independent eigenvectors, you've got infinitely many ways of choosing those n independent eigenvectors, right? Because it doesn't matter how long the eigenvector is. So the statement in the poll is definitely false. All right? As soon as you've got one way of doing this, diagonalizing your matrix, you've actually got infinitely many. There's no such thing as the eigenvectors, right, for your matrix. You can write down a collection of n independent eigenvectors if you're lucky, but they're not unique. You can take any, in each eigenspace, you can find some other basis for that eigenspace and use it instead of the vectors you've chosen from that eigenspace, or more trivially, you can just multiply them by any non-zero number you like, and you've still got a collection of eigenvectors. So the answer is false. Okay, so the previous theorem, the proof of the second half of the previous theorem does give us essentially an algorithm for diagonalizing a matrix. You just find the eigenvectors and use them as the columns of your matrix, but it's not unique. And it doesn't need to be unique. We don't care. Right? But it's definitely not unique. All right. So, let me tell you a very useful fact, which is, again, not that hard to prove, but I won't do it here. If you're curious, this is really accessible to anybody, but we'll do it in the 2025 workshops. So if you're curious, you can look up the notes for the 2025, probably next week, I would say. We'll get around to it. But the theorem states that if you've got some collection of eigenvectors, each one corresponding to different or distinct eigenvalues, then that set is immediately linearly independent. Okay? So if you've got, so this one, V1 lives in lambda 1's eigenspace, V2 lives in lambda 2's eigenspace, blah, blah, blah. VR lives in lambda r's eigenspace. You've got all your different eigenvalues. You pick an eigenvector from each eigenspace. That set, no matter how you do it, that set is independent. Okay? So in a sense, the eigenvectors from different eigenvalues are all sort of telling you different information. They're encoding different parts, spanning different parts of Rn. Okay? Now, if you didn't have the assumption of distinct eigenvalues here, this would be definitely false, right? Because you could take one eigenvector from your space, the eigenspace of lambda 1, and then you could just multiply that by 2, and you've got a second eigenvector with eigenvalue lambda 1. Those two eigenvectors are definitely not independent, right? So you've got two eigenvectors with the same eigenvalue. They may be independent, they may not, who knows? Depends how you chose them. But if you've got two eigenvectors or any number of eigenvectors all from distinct eigenvalues, that set is definitely independent. Now, one consequence of that is something that's usually sort of one of the first things people know about eigenvectors, this eigenvector business, because when it is true, well, when it does apply, the statement's always true. When it does apply, it makes life easy. But the statement is that if you've got an n by n matrix and all the eigenvalues are distinct, then A is definitely diagonalizable, right? And that follows essentially immediately now, because if all the eigenvalues are distinct, then you can write down one eigenvector for each eigenvalue. Then you've immediately got n independent eigenvectors, right? Because the theorem above says that if you've got eigenvectors from distinct eigenvalues, that set's independent. If you've got n distinct eigenvalues, you can pick n independent eigenvectors. So you can always diagonalize your matrix, because being able to pick n independent eigenvectors is equivalent to being able to diagonalize your matrix. So if all your eigenvalues are different, you've got n of them, you can diagonalize A. All right, so if all your eigenvalues are distinct, shouldn't say independent, I mean distinct. Then the previous theorem A has n independent eigenvectors. So theorem, the previous one that we just finished proving, tells us that A is diagonalizable. Now, the converse is definitely false, right? You can definitely be diagonalizable with repeated eigenvalues. So there's sort of nothing terribly special about having all your eigenvalues distinct, except that it makes life sort of easier. But there's nothing fundamentally interesting about that case. So often this business of having repeated eigenvalues gets called degeneracy, especially by physicists, but there's sort of nothing terribly interesting about it. Just a question of what's the dimension of your eigenspaces. Your eigenspaces can be bigger than one. Doesn't mean you're not diagonalizable. Okay. Is everybody comfortable so far? All right. So here's a recipe for diagonalizing a matrix. And it's basically exactly what popped out of the last proof that we did. So if you take your matrix and you find all the eigenvalues, and then you find a basis for each eigenspace, then, right, so you've got a basis for each eigenspace. All of those vectors in that basis are independent. We know that any collection of vectors from distinct eigenvalues is independent. So you can take the union of the basis of each eigenspace and you'll get an independent set. Okay? So let me say that again. So every set of eigenvectors you make from distinct eigenvalues is automatically independent because of our theorem. If you make a basis for each eigenspace, that's an independent set. So if you take the union of all these independent sets, you get another independent set, a bigger independent set. Okay? And provided the dimensions of all your eigenspaces are big enough, so that they're the geometric multiplicities. So basically from part C of the theorem we started off with this morning, that means that all of your geometric multiplicities add up to are equal to the algebraic multiplicities, and the algebraics add up to n. That means the sum of all the dimensions of your eigenspaces equals n. So if you do this business of taking a basis for each eigenspace and taking their union, you get n independent eigenvectors. Okay? And if you take that collection of n independent eigenvectors and you make a square matrix out of it, that square matrix will diagonalize A. Okay? So here's a very concrete recipe for diagonalizing a matrix. Just find all the eigenvalues, find bases for all your eigenspaces. If you stick all of those bases together and you've got n things in it, your matrix is diagonalizable, and you can use those eigenvectors to diagonalize it. If you don't have n independent things, then your matrix is not diagonalizable and you don't have to do anything else. Okay? So to diagonalize your matrix, all you have to do is solve the eigenvector problem. Find all the eigenvalues and find bases for all the eigenspaces. Now, just on the question of how to interpret what this means, I sort of made some kind of comment in this direction yesterday, but it's clearer now that we're actually talking about, you know, what specifically the columns of P mean, that they're these eigenvectors. If you think about what's going on here, right? So A, if D equals P inverse AP, it means A equals PD P inverse. And I said yesterday that every invertible matrix is a particular change of basis matrix, and that's definitely true. Because, so let's think about which particular change of basis matrix it is. So we've made the columns out of these eigenvectors, right? So these eigenvectors form a basis because they're an independent set. There's n of them, and they're in Rn. So the P's form a basis. And what I can always do is interpret any vector in Rn as its own coordinate vector with respect to the standard basis. So P1 is really P1's coordinate vector with respect to the standard basis, and P2 is really P2's coordinate vector with respect to the standard basis, etc. So what I've really got is the basis elements of this eigenbasis, and I've written their coordinate vectors with respect to the standard basis. So which change of basis matrix is this? Where am I going from? Right? The two bases involved are eigenbasis and standard basis, but which direction am I going?
From the eigenspace to the standard?
Yes. That's right. So this is P, because we've used the eigenbasis, the original basis, and we've written their coordinate vectors in the new basis. This is P from the eigenbasis to the standard basis, right? So that, I think, is the correct, most useful way of interpreting what the hell this P thing is, right? It's the change of basis matrix from your eigenbasis to your standard basis. So what's P inverse? P inverse is going back the other way. It's the change of basis matrix from the standard basis to the eigenbasis. And then if you understand that, this decomposition starts to make some kind of sense. Because what is it really saying? It's saying, well, if you picture what A does to some arbitrary vector, whenever we hit some arbitrary vector with A, we're really picturing that vector as being written with respect to the standard basis, right? Because again, every vector in Rn is sort of trivially its own coordinate vector with respect to the standard basis. So you take some vector, you want to act on it with A. Well, you can picture that as, if A is diagonalizable, first you hit it with P inverse. What does that do? It changes your vector from the standard basis to the eigenbasis. Then in the eigenbasis, all A really does is just act like D. So if you write A in the proper basis, which is the eigenbasis, it just acts like D. So the D really is doing all of the actual transformation. P inverse just sort of changes basis to a good basis first. D does the transformation for you, and then the P on the left maps you back from the eigenbasis to the standard basis. Right? So acting from the right, what we're doing is change your basis from standard basis to eigenbasis, do your transformation in the eigenbasis using D, transform back to eigenbasis to standard basis. That's really what A is doing if it's diagonalizable. Okay, so you can kind of picture D. If you picture, you can picture A and D as really corresponding to the same abstract linear transformation. A is the matrix representation of it in the standard basis. D is a representation of it in the eigenbasis. Right? So D is just corresponds to the same transformation as A, but it's written in a more sensible basis. It's really what we're doing with all this diagonalization stuff. It's changing to a better basis. Okay, did that make any sense? Okay, all right, one thumbs up, that's good. All right, so who cares? That's sort of a theoretical interpretation of a way of understanding what all this diagonalization stuff means, but how is it actually useful? And one thing it is actually useful for is taking high powers of your matrix, okay? And you could also ask who cares about that, and I'll give you an answer to that who cares in a minute. But for the time being, let's just assume that we might want to take the 100th power of a matrix. Now, very often you actually really do want to do that, but let's just assume that that's something we want to do for the time being. So you could ask the question, how on earth would I take, even this very simple example that we've been looking at, 2112, how would I take the 100th power of that thing? Right? You certainly don't want to do it by hand. You could stick it in Mathematica and ask it to, do A.A.A.A 100 times, right? Or I think there's actually a matrix power function in Mathematica. So Mathematica could do this for you. But is there a better way? And the answer is, if A is diagonalizable, there's a much better way. And you start off by diagonalizing it. So we know A has eigenvalues, what do we say, 3 and 1. With eigenvectors P1 and P2. So if we want to diagonalize it, what do we do? Well, we use the eigenvalues as the diagonal entries. And note here, there's, D is not uniquely specified, right? Because I could choose it to be 3, 1 on the diagonals instead of 1, 3. Doesn't matter. But whatever you choose, that ordering is arbitrary. But whatever you choose, you've got to choose the same ordering for the p's, right? Because in that proof of the fact that this matrix of eigenvectors diagonalizes your matrix, what we're using is that pi was an eigenvector corresponding to lambda I. Okay? So as long as you order the eigenvalues the same way you order the eigenvectors, it's fine. Doesn't matter, just do the same. Just be consistent. So if we choose D to be that, then we no longer have any choice. We have to make P be this. And we know that A equals P, D, P inverse. So if we try and calculate A to the 100, we really have something that looks like this 100 times. And the sort of hand-wavy version of this is that every internal pair of P and P inverses are going to be sitting next to each other, and so they eat each other, right? You've got one P sitting on its own on the left and another P inverse sitting on its own on the right. But every internal pair is going to be sitting next to its inverse, and so they zap each other and they disappear. So all these internal P's disappear. And what do you get? You get P. Now the D's don't disappear. How many D's have I got? I've still got 100 D's because I started off with 100 A's. This is P times D to the 100, P inverse. Now you can turn that hand-wavy argument about people eating each other into an inductive proof, and you should do that on the problem set. So this is a very general result, right, that if A is diagonalizable, A to the K is P, D to the K, P inverse. Okay, it's quite easy to prove by induction, and that's all that we're using here. And the good thing about this, what's the good thing about that? Why is it better to have, we've still got a 100th power of a matrix here. Right? We're trying to compute the 100th power of A, and now I've replaced that with 100th power of D, plus 2 extra matrix multiplications. So why have I actually done anything useful?
It's easier to find the power of the 100th power of D because it's just eigenvalues. Where it's on the diagonal, so we can just put it power of 100.
That's right. So the point of taking powers of diagonal matrix is that the kth power of a diagonal matrix is just another diagonal matrix where all the diagonal entries are the kth powers. Okay? So it's a trivial exercise. And you can prove that too on the problem set. Okay? But this is why it's useful. The kth power of any diagonal matrix is super easy. You just take the kth powers of the diagonal entries. Not because I told you that's true, because you can prove it. Okay, so if you do this, what do you get? For A, you get the following thing. Now, it's still written in terms of things like 3 to the 100, and I'm not going to try and simplify what 3 to the 100 is, because you can't. It's just 3 to the 100. But that's a little 2 by 2 matrix with really explicit entries. Okay? And if you tried to do that any other way, it would be horrible. All right. Is everybody happy? So we know how to diagonalize matrices, and we know at least one good reason why you might want to diagonalize matrices. Okay? That's taking high powers. Now, the next question is, why on earth would you be interested in taking high powers of matrices? And there's multiple reasons. And they're all sort of, in some sense, coming from the same place, because lots of interesting structures in maths are sort of defined recursively. But one really concrete situation where this arises is the study of Markov chains. So who's seen Markov chains before? Okay. Sort of. Some people sort of. Okay. So Markov chains are a topic in probability theory, and they're one of my favorite things. And first of all, who knows the difference between statistics and probability theory? Yes, right? So the short answer to the difference between probability theory and statistics is everything. Right? So statistics needs probability theory. Probability theory does not need statistics at all. Statistics is about how to understand data using probability theory. Probability theory is just sitting on its own, the branch of maths doing its own thing. It doesn't care about data at all. One of the things it does care about is stuff like Markov chains. So the whole point of probability theory is to understand or model mathematically the evolution of random processes. Okay? That has nothing to do with data or statistics. We're going to look at one of the simplest examples of these things. So if you want to learn more about this and you haven't taken MTH 2222, I strongly recommend you do that, even if you're a pure math student. It's got nothing to do with statistics. It's got lovely objects in it like this. Okay, so that's my rant about probability theory. Now, what are we going to particularly study? We're going to study effectively the simplest sort of object, interesting object that you can imagine that sort of evolves in time in a non-trivial way, but in a random non-trivial way. So what kind of objects do we need? Well, all we really need from probability theory, and it doesn't really even involve anything from probability theory except a word, is that we're going to consider a thing called a distribution. Right? So for each fixed t, forget about t for the time being, for each fixed t, we're going to say that our system, whatever it is, has some probability of being in one of n states. Okay? So your system can be in one of n states, where n is finite. So x1 of t is the probability of your system being in state 1. x2 of t is the probability of your system being in state 2, blah, blah, blah. So what does t do? T is supposed to represent time somehow. So we've actually got a sequence of all of these numbers. And a probability, all you need to remember from probability theory from high school, is that probabilities are non-negative, and the probability of being in one of your states should be 1. Okay? So at least one of your states, the probability has to be 1. So if you add up all of these n numbers, you should get 1. So this collection of probabilities, x1, x2 up to xn, they're just non-negative numbers that add up to 1. That's all you need. And since we've got this collection of n numbers, you can make a vector out of them. If you make a vector out of them, we say we have a probability vector. So a probability vector is just a vector whose entries add up to 1, and all the entries are non-negative. Now, what's t do? T is supposed to sort of represent time. So we really think of, actually, we haven't just got one of these vectors, we've got a sequence of these vectors. Okay? So we've got an x1, and we've got an x2, blah, blah, blah. Each of those is vectors. Okay? X of 1, x of 2, x of 3, etc. And so we picture x of t as being the distribution of our system at time t. Right? So x1 of t tells you the probability of being in state 1 at time t. And maybe that probability changes. All right, so let's look at an explicit example of how that might change. So this is a very simple problem or a situation that we're trying to model about a mathematician that likes eating sushi and pizza. Right? And before the pandemic and before all the interest rate rises, this sort of did model me because I was able to afford to go out for lunch, but I don't anymore. This mathematician only eats pizza and sushi. Right? So there's two states. The states that we're talking about are what the mathematician has for lunch. And it's either pizza or sushi, but the decision is random. Okay? So if we're trying to think of probability vectors, we're going to have n equals 2 here, right? And we're going to try and understand how this evolves with time. Because even though the choice of what I have for lunch or what this mystery mathematician has for lunch is random, it's not completely independent of what they did the day before, right? So the rule is, if they eat sushi on a particular day, then on the next day they eat sushi again with probability of half, or they have pizza with probability of half, right? So if they have sushi, the next day's decision is completely random, right? Uniformly random. But they don't like eating too much pizza because they know it's not good for them. So if they had pizza on Tuesday, then on Wednesday they'll definitely have sushi. Okay? So this is the rule. If you eat pizza on day t plus 1, you have to have sushi. If you eat sushi on day t, you can do whatever you like the next day, randomly. Okay? You flip a coin. All right, so there's going to be an x1 of t, which is, you can either define it to be pizza or sushi, whatever you like, but let's define it to be something to be concrete. So let's say x1 of t is the probability of eating sushi on day t, and x2 of t is pizza. So because of the rule of how this evolves, there's a recursive structure, right? I can understand the probability of what I eat on day t plus 1. So the probability of having sushi on day t plus 1 is something or other times the probability that I had sushi plus something or other else times the probability I had pizza. Okay? So if I had sushi on day t, what's the probability of having sushi again on day t plus 1? A half. And if I had, sorry, that shouldn't be 1, that should be a 2. If I had pizza on day t, what's the probability of having sushi on the next day? 1, right? So this is a 1. So this is the probability of eating sushi on day t plus 1 in terms of the probabilities of what I was doing on day t. So we've got this recursive structure. We understand what's happening at time t plus 1 in terms of what was happening at time t plus 2. Now what's the probability of having pizza play the same kind of game. So if I had sushi on day one, sorry, on day t, what's the probability of having pizza on day t plus 1? Half. And if I had pizza on day t, what's the probability of having it day t plus 1? 0. Okay? So we completely describe the state, well, the distribution, not the state, but the distribution of time t plus 1 in terms of the distribution of time t. And so you can write this in vector form if you like. And then you stare at it and you realize, all right, xt plus 1 is some transformation of xt, and in fact it's a linear transformation. Right? So you can easily, and we know all linear transformations, Rn to Rn, are actually matrix transformations, so you can factorize out a matrix that's doing all the work for you here. And if we want to write that in vector notation again, we can, where we've got this matrix we're introducing, which is just this thing sitting here, half 1, half 0. Okay, so we've got, in this particular example, that x of t plus 1 is just p times x of t. Yep.
Since it has like a half power, sorry, like a half in there.
Yep.
If you were to take like a certain power, would it eventually kind of, what's the term, like just kind of stop or like go to a certain value?
Yes. So we're going to see something like that. Yes. So it doesn't, I mean, all of the numbers in this kind of matrix are going to be between 0 and 1, right? Because they're all probabilities of something or other happening. A good question to ask, if you want to understand what happens in the long-term behavior of x, is it's going to end up that we need to look at high powers of p, right? And so that'll mean something about high powers of these entries. It's not completely trivial, that question, because sometimes the tth power of p will converge and sometimes it won't. So you need p to have some nice properties, but we'll talk about that. But that's the first natural good question to ask, is how does this behave for large t? Okay. So now the first question we ask here is slightly more pedestrian, which is not what happens at infinite time, but just what happens on Thursday, right? So if the mathematician happens to have pizza on Monday, what's the probability they have pizza on Thursday, right? That's a practical question that people have to ask or answer for themselves. So let's let, because t doesn't really matter, let's let Monday be day t. You could also pick it to be day 0 if you like, doesn't matter. But Thursday is then day t plus 3. And we're saying that you definitely have pizza. So if you definitely have pizza, what does that mean your distribution is? It means it's 0, 1. Right? Because the probability that you had sushi on day t is 0. The probability you had pizza was 1, because you definitely had pizza. So when we say definitely had pizza, this is really what we mean mathematically. Okay? And we can then work out what x of t plus 3 is, because it's p x of t plus 2, and that's p times p of x of t plus 1, and that's p times p times p of x of t, right, which is third power of p times x of t. And computing the third power of p is not super hard. You can just do that. and you find that the probability of having sushi is 3/4 and pizza is 1/4 on Thursday. So the probability of this person eating pizza on Thursday, given that they had it on Monday, is only 1/4. Right? So you see that in the long term, there's definitely a preference for having sushi rather than pizza, which is not surprising. But you could ask the question, and we will talk about this probably next week now, what's the sort of, is there a sensible limit to this thing as t goes to infinity? And if so, what's sort of the limiting probability of eating pizza after a really long period of time? Right? So if you know you ate pizza for lunch in 1947, what's the probability that you're going to have pizza tomorrow? You can answer that sort of question. Okay? All right. So let me just give you a bit of, I guess, jargon, for want of a better word, to put what we've just looked at into a broader context. So this matrix that we saw is an example of a thing called a stochastic matrix, right? So P is a stochastic matrix. And what is a stochastic matrix? It's a matrix where all of the columns are probability vectors, right? That's all it is. So a probability vector is a vector where all the entries are non-negative and add up to 1. A stochastic matrix is just a matrix that you make out of probability vectors, using the probability vectors as columns. Now, our process satisfied this kind of recurrence. So x of t plus 1 was p times x of t, where p was some stochastic matrix. Any random process that satisfies that, so any process where the distribution satisfies a recurrence like this, is called a Markov chain. And this is sort of the simplest, non-trivial way of introducing time dependence. Right? So your process has some kind of memory. It knows what it did the day before, and that affects what happens on the next day. And we call P the transition matrix of that Markov chain. So the difference between stochastic and transition matrix is, I guess, a question of how you use the word. All transition matrices are stochastic. Right? Stochastic is just saying all of the columns are probability vectors. Right? So all transition matrices are stochastic. But when you talk about a particular Markov chain, you ask the question, what's its transition matrix? And its transition matrix is the matrix, the stochastic matrix here, that turns up in this recurrence. Okay? And the interpretation of the entries of this transition matrix are that Pji gives the probability of moving from state I to state j, right? And that seems a little bit backwards, right? It'd be kind of nicer if Pij was the probability of moving from I to j. And probabilists actually do things in that direction, but then you have to replace everything with sort of the transpose of what we've got. And so your column vectors aren't column vectors anymore, they're row vectors, and there's, you sort of make the appropriate changes, and then you have to deal with everything being in terms of row vectors. So we're not going to do that because I'd have to generalize in an uninteresting way all the eigenvector stuff we did. So we're going to interpret, we're going to write our recurrence like in equation 6.2. And then if you do that, the interpretation is Pji is the probability of going from I to j. So you sort of have to read it right to left. Okay, now, final observation is that if you have a Markov chain, x of t is just p to the t times x of 0. So that's a really simple inductive proof. So 6.3 holds by definition for t equals 1. If it holds, otherwise you wouldn't have a Markov chain. If it holds for some t that's at least 1, then x of t plus 1 is p x of t, and by the induction hypothesis, this is p times p to the t x of 0, and so that's p to the t plus 1 x of 0. Okay, so the simplest inductive argument you could possibly hope for. But this is a nice result, right? So the definition of a Markov chain is just any old sequence of distributions that satisfies this recurrence. But what that immediately implies is that, in fact, if you want to know x of t, you just need 2 ingredients. You need to have good understanding of what the teeth power of your transition matrix looks like, and you just need to know what your initial distribution was, what x of 0 was. Okay, so this is giving motivation from probability theory to understand things that look like high powers of some stochastic matrix. Okay, so we'll continue talking about that next week.